This is arrows in chemistry part 2, and these arrows are more common in organic chemistry. Number 7. The stereochemical arrow. This arrow is used to identify the absolute configuration, the actual arrangement of atoms or group of atoms around a chiral center as R or S. A chiral center is an sp3 hybridized carbon with 4 different groups attached. There are 2 possible different spatial distributions of these 4 different groups. This gives 2 possible optical isomers. These optical isomers are called enantiomers if an imaginary plane was between the 2 molecules. They are related as a mirror image of one and another. Also note, these molecules are not superimposable, as there are no internal plane of symmetry. More about this in a separate video. To identify the 2 different optical isomers, rank the atoms or group of atoms attached to the chiral center in order of priority based on atomic number, starting with the atom directly attached to the chiral center. This follows the Cahn-Ingold-Prelog rule. The number 1 is the highest priority, and that is associated with the highest atomic number. The lowest priority is the lowest atomic number. Rotate the molecule so that lowest priority is in the back. There are now 3 points, like that in a steering wheel. Draw an arrow starting at point 1 and finishing at point 3. If the arrow goes clockwise, then the absolute configuration is R, and if it goes counterclockwise, then it is S. This is an animation of the R stereochemistry for 1-bromo, 1-chloroethane. The bromine atom is colored red, the chlorine atom is colored green. Bromine has the highest atomic number. This is the S stereochemistry animation for 1-bromo, 1-chloroethane. Number 8. This is the resonance arrow. This arrow is aligned with 2 opposite full arrowheads. It indicates that between the electron dot structures, or Lewis structures, both represent the actual true structure of the molecule. Each representation is either significant or insignificant. Between structures, only shift in electrons occupying p orbital to an adjacent p orbital occurs, and atom connectivity does not change. For this part, you will need to watch the full video on resonance structures. This is an example of resonance structures between 2 allylic cations. Which one do you think is the more significant structure? Review the video on resonance structures. Number 9. Curved arrows to show electron flow. There are 2 types of curved arrows, and these are used to show electron flow between 2 structures, either between resonance structures, or from reactants to intermediates, or from intermediates to products. First, the full arrowhead curved arrow, not to be confused with the stereochemical arrow. The other type of arrow is the half arrowhead, the so-called singly-barbed arrow. This arrow represents the single electron for radical reaction mechanisms. The full arrowhead. This shows the movement of 2 electrons. It can be used to show electron flow between 2 resonance structures, or it can be used to show electron flow in a reaction mechanism. The tail end is where there is an electron-rich region, where there are a pair of electrons. It can be a lone pair of electron or covalent bond. The arrow points at the electron poor atom to give it a lone pair, or to a bond to make a double or triple bond. Here is an animation of the process. As you draw the arrow on paper, this is how it would go, and the final result is what is reported. This is an animation of curved arrows between resonance structures. The main carbons involved are labeled with numbers. I have drawn the full structures here, but you should try to get used to the line structures without the carbons or hydrogens drawn in. Note that the 3 carbons involved are labeled 1 to 2 to 3, and all have p orbitals. Each of these 3 carbons are all sp2 hybridized. C3 has an empty p orbital and there is a formal positive charge. On shifting, the formal charge is an arbitrary number that represents the number of electrons around the carbon atom. It does not pick up and shift. It is determined after the electron shift has occurred. It is possible to push the pi electron from C1 to C2 to make a lone pair on C2. The C1 and C3 will both have positive 1 formal charge, while C2 has a negative 1 formal charge. This resonance structure is possible, but would be considered insignificant because there are too many formal charges present. The lone pair on C2 will then shift to a pi bond between C2 and C3, with C1 having a formal positive charge at the end. This next video, there's a fatal mistake in the curved arrow mechanism. Surprisingly, this is a common mistake in organic chemistry by students. Often it is shown that the hydrogen migrates. The HCl bond is polarized so that hydrogen is least electronegative or electron poor. The arrow should not start here and point towards the electron-rich nitrogen. The next animation is the correct mechanism for protonation reaction. This is a common reaction in organic chemistry. The arrow starts with the lone pair on the nitrogen, then this will attach to the hydrogen, which then releases the chlorine. For this animation, the hydrogen doesn't need to switch places with chlorine because the 3D structure around the chlorine with the lone pairs is actually tetrahedral. Just for simplicity, I animated this so that the hydrogen goes to the right of chlorine so that it can be extracted by the lone pairs on nitrogen. The half arrowhead, or singly-barbed arrow, shows the movement of one electron called a radical electron. This can be used to show the mechanism or the electron flow in radical reactions involving initiation, propagation, and termination. Full details are available in a separate video. The tail end is where there is a single radical electron or bond. The half arrowhead points at an atom to show the formation of a radical or to create a bond if 2 radicals combine. This animation shows the initiation process. It involves a light source that initiates the process, or heat can be used to break the weak chlorine-chlorine bond, which is 243 kilojoules per mole, to make 2 radicals.